Speed. In its fundamental kinematic sense, a very simple story. A vector tangent to the trajectory with its components, the time rates of change in the x, y, and z coordinate of an earthbound system. A version where we neglect the vertical dimension is called ground speed by aviators, and it is useful, of course, in working out the time it takes to cover the distance between 2 points on a map. This purely kinematic version of speed, the three-dimensional variety, is also what we need for calculating kinetic energy, and its time derivative is the acceleration that goes into the inertial terms of all the equations of mechanics of flight. Now, up to here, we might as well be in vacuum. But once we start accounting for the presence of air, an important ingredient in preventing the Earth from coming up to hit the aeroplane, a couple of awkward twists ruin this simplicity. First, wind, which moves the coordinate system. Second, the physics of the atmosphere varies in space and time, and with speed itself as we approach the speed of sound. And it's these twists that bring in a series of often badly misused and frequently misunderstood quantities of the speed variety. It doesn't help that some of these aren't even really speeds, they're more like pressures measured by a Pitot-static system, which we read as speeds. In this video, we explore these and we look at how they're measured and or calculated, and through examples we look at how one can be converted into another in practice in a Python world using ADRPy. If there's a single key takeaway from what follows, it is this. In aeronautics, the word speed on its own, without a precise qualification of which variety we mean, is about as useful as your doctor only writing on your prescription the words, "Take 2 tablets per day." We've already seen that the ground speed is the speed at which the vertical ground projection of the aircraft moves with respect to the surface. And now our first and simplest type of airspeed, the true airspeed, is simply the speed at which the air molecules in the far field, so far enough to be unaffected by the presence of the aircraft, pass the aircraft. When there is no wind, which is basically almost never, the ground speed and the true airspeed are the same. When there is wind, the ground speed becomes the vector sum of the true airspeed and the wind speed. Let's visualize this vector equation. TAS is the speed of the flow seen by the aircraft, seen in an aerodynamic sense of the word, and when flying without any side slip, which is a reasonable approximation most of the time, the direction of the true airspeed vector is basically the heading of the aeroplane. That is the direction in which the nose is pointing. Now, when wind is present, it makes no difference in the aircraft's frame of reference, but the frame of reference itself is translated with respect to the ground at the speed and in the direction of the wind. So, in the ground frame of reference, where we are assembling the wind triangle or speed triangle if you like, the aircraft will be following a track with a course that is different from the heading, the difference being the so-called crab angle. And once again, we can see from this picture that as long as the speed and direction of the wind doesn't change abruptly, wind is only of navigational relevance. It makes no difference to the aerodynamics of the aeroplane. Aircraft on crabbing crosswind approaches, such as this 777 on a 27 left arrival into Heathrow in a crosswind from the left, provide a neat illustration of the speed triangle with the sum of the true airspeed aligned with the fuselage axis showing the heading and the wind speed vector, resulting in a ground speed vector aligned with the track of the aircraft, being in this case an extension of the runway centerline. It is often desirable to minimize the ground speed, that is to flatten the wind triangle onto itself such that the ground speed side all but disappears. This Custer channel wing aircraft, developed by a team led by Professor Andy Keane at the University of Southampton, is capable, by virtue of its huge maximum lift coefficient, of true airspeeds that are often close to even low-level wind speeds, thus allowing the aircraft to practically hover into a headwind and make a near-vertical landing. Sometimes, such as when cruising at high altitudes, the goal is to flatten the triangle in a way that makes it as long as possible, that is, to have a tailwind help us along. It's not uncommon to add 200 knots to the ground speed of a transatlantic crossing this way, resulting in ground speed in excess of 700 knots. But of course, aligning flight paths with the hugely chaotic wind patterns of our planet is not an easy task, as illustrated by these North Atlantic flow snapshots taken at surface level, 5,000 meters and 10,500 meters. So what does all this look like to the pilot of a modern aircraft? Most glass cockpit aeroplanes will have a compact visualization of the key elements of the wind triangle, looking something like this. When planning a flight, depending on the circumstances, you'll know different elements of the wind triangle as forecast. Calculating the unknown elements is relatively straightforward by breaking out some basic trigonometry. You could use something like the law of sines or the law of cosines. Or if you're feeling nostalgic about a more analog era of aviation, you could use a pencil and the so-called wind side of one of these flight computers. Nowadays, pilots are more likely to be using the wind side of an iPad, taking their pick of several super flight planning apps out there. You could also use ADR-Pi to do a lot of wind-related calculations in a more Pythonic fashion. Let's consider this simple example from the ADR-Pi documentation where we are given a METAR and we are to calculate the wind components on runway 09 at Yeovilton. First, we import the atmospheres module from ADR-Pi as well as a package called METAR. Next, we create an object of the runway class. This class is defined in the atmospheres module, and we instantiate one of these simply by passing the IKO identifier of the airfield as well as the ordinal number of the runway within that airfield. We next parse the METAR using the METAR package. In this case, we simply want to extract the wind direction and the wind speed. Of course, it would be really easy to just eyeball the wind group from this METAR and get the numbers out manually. But if you wanted to process a huge number of these, say a data set of tens of thousands of METARs, then this type of automation could come very handy. We now deploy the wind components method applicable to objects of the runway class, where we simply pass this wind direction and the wind speed, and then it returns the runway component and the cross component of the wind. We began our survey of speeds used in aviation with the simplest of them all, the true airspeed. So how do we calculate the true airspeed? We use, surprisingly enough, something called the airspeed equation. V true squared equals 2 gamma over gamma minus 1 times P static. That's the static pressure at the location of the aeroplane, divided by rho, which is the density at the location of the aeroplane, times P impact. That's the impact pressure measured by the Pitot-static system of the aircraft, divided by P static plus 1 to the power of gamma minus 1 over gamma, gamma being the ratio of specific heats, which is usually taken as 1.4 for air, minus 1. So that's the true airspeed. Now, one of the issues with this equation is that the only thing we can reasonably reliably measure is this impact pressure from the Pitot-static system. In fact, on a simple aircraft, most light aircraft, the airspeed indicator really is a pressure gauge. It's just a pressure gauge that displays this impact pressure, and the airspeed indicator is calibrated in units of speed, simply because units of pressure are not particularly intuitive when we want to pilot an aeroplane. So what we have displayed on the airspeed indicator is, on a simple mechanical airspeed indicator, is the indicated airspeed. Which is going to be 2 gamma over gamma minus 1. We don't know the static pressure, so instead we're going to use the value of the ambient pressure at sea level on a standard day, and similarly we don't know the density at the location of the aeroplane, so we're going to use the density at the sea level as a sort of 0th order approximation here. And then we're going to have the impact pressure divided by P0 plus 1, gamma minus 1 over gamma minus 1. Now, one of the issues with this is that it is going to, its accuracy is rather going to depend on the accuracy of the impact pressure, which in general it isn't great, especially due to errors associated with the measurement of static pressure. So the location of the static port, the static source component of the pitot-static system, is going to have a significant impact on the accuracy of this. Now, if we are able to calibrate this value in some way, then we end up with something we call calibrated airspeed, which is going to look very similar in terms of its equation. We're still assuming sea level values for everything here, but we're going to have a sort of an improved version of this. I'm going to denote that with a pi asterisk, sort of a more accurate version of the impact pressure, which accounts for positioning errors in the pitot-static system, in particular when it comes to the positioning of the static source. So what we've done here is we've corrected for positioning errors. This is only really possible on computerized aircraft that have an air data unit and have some type of digital display that is able to do the correction between pi and pi asterisk. Now, this still isn't the genuine article, because it still has the sea level static pressure instead of the actual static pressure. So if we replace that with the actual static pressure, we end up with something called EAS, or equivalent airspeed, which has an actual static pressure. It has this improved impact pressure, and again the static pressure. And now this is pretty close to the true airspeed. The only difference being that we still have this rho 0 instead of rho. So we can express that by writing the true airspeed simply as the equivalent airspeed divided by the ratio of those two densities, which is sometimes the square root of, which is sometimes denoted by sigma. Below Mach 0.3 or so, we have the luxury of assuming the flow to be incompressible, and that rather simplifies the algebra. We can write the impact pressure, which is that difference between the total and the static pressure measured by the Pitot-static system of the aircraft, as a dynamic pressure of the form half rho Vt squared, where rho is the ambient density at the location where the aircraft is flying and Vt is the true airspeed, which allows us to write the true airspeed simply as the square root of 2pi over rho. Now, because of the difficulties in measuring rho, we are going to calibrate our pressure gauge, which is effectively what our airspeed indicator is, to show an indicated airspeed using an equation of this form, where rho 0 is the sea level standard value of the density. Now, if we enhance our accuracy of the impact pressure by accounting for positioning errors, we can write a calibrated airspeed, which in this case will be the same as the equivalent airspeed as 2pi asterisk, signifying that more accurate value divided over rho 0. The true airspeed can thus be written as V equivalent over the ratio of densities in exactly the same way as we did in the case of the compressible flow. Another way of writing this is half rho Vt squared is equal to half rho 0 V equivalent squared. So if we're flying at a true airspeed Vt in ambient density rho, yielding a dynamic pressure Q of half rho Vt squared, then the equivalent and the calibrated airspeed for that matter is the answer to the question, how fast would we have to fly at sea level in standard conditions to get the same dynamic pressure Q? The fact that a typical basic airspeed indicator is really just a dynamic pressure gauge is no particular hardship, because most of the really important stuff in the mechanics of flight, for example, the amount of lift an aircraft is capable of generating, is really a function of dynamic pressure rather than speed per se. Similarly for drag. The answer depends on how high and how fast you're flying. Here is a chart of differences between calibrated airspeed and equivalent airspeed across a range of altitudes and speeds. Below about 200 knots and 30,000 feet, the difference is under 5 knots, but exceed either of those limits and you could be wrong by up to 6 or 7%, with calibrated airspeed always being higher by that margin. Check out the ADR-Pi GitHub page for the Jupyter notebook I used to generate this graph with ADR-Pi's EAS to CAS conversion method. Here are the position errors for the Pitot-static system on a fairly typical single-engine piston light aircraft. A couple of takeaways. One, the difference can be up to 5% or so. 2. Deploying the flaps changes the position error. This is one of the main reasons why showing calibrated airspeed is impractical on simple aeroplanes with mechanical gauges. Such variations would be extremely hard to encode in the linkage between the pressure bellows of the airspeed indicator and its needle. Now, this aircraft has an alternate static source that can be selected by the pilot. For example, in case icing is suspected on the primary static port, the alternate source is inside the cabin, which is of course unpressurized. Here are the errors for the alternate static port. Again, a couple of things to note. The variations associated with flap deployment are a little larger, up to 10% or so. And the variations between readings taken with two different static sources can be quite significant. For instance, the error at 160 knots indicated can go from 3 knots to 7 in the clean configuration when switching to the internal port. Through the magic of flight simulation, explained in this case, let's run some quick illustrative numbers on this 747 cruising at Mach 0.8 at 40,000 feet. After loading ADR-Pi's atmospheres and unit conversions modules, we instantiate a zero offset standard atmosphere in an object we call ISA. We enter the Mach number and the cruising altitude of this aircraft, and we convert the cruising altitude from feet to meters because we will be needing that shortly. So the unit conversions module. Next we calculate the speed of sound at 40,000 feet in the current atmosphere. There are a couple of methods we can use for this. Next we calculate the true airspeed, which is simply the Mach number multiplied by the speed of sound we have just found. And we calculate the equivalent airspeed, and there is a method for that, converting TAS to EAS, applicable to objects of the atmosphere class. Similarly, we can now calculate the calibrated airspeed, converting back from the equivalent airspeed, and again there is a method for that in the atmospheres class, and we end up with 242 knots calibrated. Now let's jump into the cockpit and check our numbers. You can see that we are pretty close, except that we are a tiny bit above our target Mach number. So we enter 0.802 at the top and rerun the calculations, yielding 243 knots, which is exactly the calibrated airspeed shown in the little window on the airspeed tape on the left. Also, we see our true airspeed as expected, shown as 460 knots in the top left corner on the navigation display. We set the simulated atmosphere to feature no wind at this altitude, so the ground speed is also 460 knots. Now, it's worth mentioning here that the speed displayed on the speed tape is commonly referred to as the indicated airspeed, but on fancy glass cockpit aircraft such as this one, it is actually almost always a calibrated airspeed. Note also that as we are at Mach 0.8, well into the compressibility zone, this is close but not equal to the equivalent airspeed, which we just calculated as 228 knots equivalent. Now, let us imagine that we have descended by 5,000 feet to 35,000 feet, but we are maintaining the same Mach number of 0.8 or so. As we jump into the flight deck, first we note that the true airspeed is broadly the same, 460 knots, actually accidentally exactly the same, with the tiny shortfall in Mach number cancelled out exactly by the minimal change in temperature and thus in speed of sound between flight levels 400 and 350. As expected, the calibrated airspeed has increased by a significant margin of nearly 30 knots. The ambient density here is about 25% greater than it was 5,000 feet ago. Plus, note on the little graphic in the corner of the navigation display that with a 100-knot headwind we have just thrown into the simulation nearly on the nose just for fun, the ground speed is now down to 363 knots. Speed in aviation is a long and wonderful and complicated subject, and we only scratched the surface here with some basic definitions and examples. Many fascinating aspects will have to remain for another time. We have seen that a key source of complexity is the variability of the physical parameters of the atmosphere in space, particularly with altitude, and time with weather. Check out ADR Shorts 1, which is all about atmosphere models. Remember, the word airspeed or speed on its own conveys no useful information, and in aviation, pedantry always pays off. For sloppy users of the word, speed will merely be a measure of how quickly they can get to the scene of the accident. Thank you for flying with us, and happy designing!